Yeah, we'll start it now. So today we're going to start with the Taylor's expansion series. In the Taylor's expansion series, yeah. So Taylor's expansion series you might have studied in your mathematics, but we'll put it in the form of our convenient form how we can use this Taylor's expansion for the what we call it as for optimization function. Okay. Yeah. See, a function which can be approximated by polynomials in a neighborhood of any point in terms of its value and derivatives using Taylor's expansion. In the sense, the Taylor's expansion is just a function. So if you can have a point you can approximate by using a polynomials, which will just near neighborhood of the point and its value and its derivatives can be approximated using a polynomials which using the Taylor's expansion. Let us consider a function f of x of one variable. Taylor's expansion for f of x about the point x star. Okay, so please make a note of this equation. F of x is equal to f of x star plus differentiation of f of x star with respect to x into x minus x star. Okay, plus half dou square d square f by dx square d square f of x star by dx square x minus x star whole square plus r. So this is the Taylor's expansion for the first function, of one variable. So we are talking about Taylor's expansion for two different cases. One is for function for one variable and second one is for two variables. Okay. So this is the expression for the Taylor's expansion series for the first function of one variable. Okay. Here, in this case, please make a note of this equation. These equations are very much required for us. So when we are solving the problem. Okay. So where r is a remainder term that is smaller in magnitude than the previous terms if x is sufficiently close to x star. So in this equation, you can see the term r. So r is just a reminder term, and this term is always being smaller in magnitude than the previous terms if x is sufficiently close to x star. So this is what the r terms, and here let if x minus x star is equal to d. So we have put what we have here is a small change in the point x star. Taylor's expansion becomes a quadratic polynomial in D. So what we are doing here is we can approximate a function using a polynomials. So I think polynomials, you know how to what is polynomials. So when a function is approximated in the neighborhood of any point in terms of its value and derivatives, okay, and using Taylor's expansion. So this is for the expression of expansion what we have written it for a single variable or a function having a one variable. Okay, so here, so when we just consider x minus x star, the small change in the point x star, in the sense when you take an x star a very close, the next point to the x in the vicinity of the x function f of x, then the Taylor's expansion will become a quadratic polynomial in D, where x minus x star is equal to D. We just represent it as a D. So therefore, so here, please make a note of this equation. I'm just moving to the next slide now. So now in terms of D, so the function that is Taylor's expansion will be in this way. So please make a note of this, where D is the small difference in the x star. So f of x star plus D is equal to f of x star plus differentiation of f of x star to with respect to dx into D plus half into d square f of x star by dx square into d square plus r. Please make a note of these things. Please take a sheet of paper and keep on writing, note down these equations. Okay. So how we are just framing the Taylor's expansion series into according to our convenience so that we can easily understand the optimization part. So these are the two equations what we are discussing. It is for a function having a single variable. Now the second thing what we go for a function which is having a two variables, which is in the function in the form of x1 and x2. The Taylor expansion at the point x1 star comma x2 star. So in the previous equation, we have taken a single variable as x. Now we are taking a variable as a two variable, which is in the form of x1 and x2. Right? So now, how we can, if we approximate the two points just the neighborhood of x1 and x2 as in the form of x1 star and x2 star, and how we can write the Taylor's expansion series for us. So Taylor's expansion, it will become f of x1 comma x2 on the LHS part, which is equal to, let's make a note of these things, all these equations properly, don't do mistakes here. Yeah, f of x1 star comma x2 star plus partial differentiation of f with respect to x1 into g1 plus partial differentiation of f of x2 with respect to g2, x2 and d2 plus. So this is what you can understand over here is, so how the Taylor's expansion changes with respect to the two variables. Okay, so please make a note of these equations correctly. Don't do mistakes here. Correctly note it down. Everything is very important at the end. So why? Because we will be landing into a one standard format in the form of a vector gradient and in the form of a Hessian matrix. So that's why it is very important for us now. Okay. So please make a note of all these things clearly. So here, where d1 and d2 in this expression, what we are getting is d1 and having some connectivity problems. I'm sorry. Yeah, just continuing now. So here, so I was just talking about the Taylor's expansion for two variables. Okay, so this is the equation what I was talking about. Okay, so where d1 and d2 are x1 minus x1 star and d2 is x2 minus x2 star. Here, all the partial derivatives are calculated at the given point x1 star and x2 star. For notational compactness, the arguments of these partial derivatives are omitted in the equations, and in all the subsequent discussions, Taylor's expansion in the above equation can be written using the summation notation. Okay, so we will go to express the same form in the summation notation. So the Taylor's expansion can be written in this form. F of x1 comma x2 is equal to f of x1 star comma x2 star plus summation of. So please make a note of this. Okay, so here we are expressing the Taylor's expansion in the form of a summation. So please make a note of this. This is very important for you. This format is very important for us. So please make a note of this. Hope you might have noted down this. So this is the Taylor's expansion series for two variables in the summation notation. Okay. Here, recognizing the quantity dou of x star f of star by f of xi as the components of the gradient of the function given in the above equation. That is what we call it as a gradient vector. This is a gradient vector, and this dou square f of by dou x square as an Hessian evaluated at the given point x star. Taylor's expansion can also be written in the matrix notation. So what we are doing here is, so we have written the Taylor's expansion for two variables. Okay. So in the neighborhood of x1 star and x2 star, and we have expressed the Taylor's expansion in the summation notation. Now, just identifying or recognizing the vector gradient as well as Hessian matrix in this Taylor's expansion, we are expanding, we are expressing the Taylor's expansion in the matrix notation. Okay, so how this Taylor's expansion can be expressed in matrix notation? So we'll go to discuss in the next slide. This is the one. Able to get it? So f of x star plus d is equal to f of x star plus delta f of t into d plus half into d transpose of d into h into d plus r, where h is the Hessian matrix and del of f is the gradient vector for us. So where x is equal to x1 minus x2 in comma x star is equal to x1 minus x star minus x2 and d is x minus x star, where h is 2 cross 2 Hessian matrix. Note that with the matrix notation, Taylor's expansion in the above can be generalized into functions of n variables. In that case, x, x star and gradient of f are n-dimensional vectors, and h is then n cross n Hessian matrix. N cross n Hessian matrix. Hope you people are following. So please, this is totally, it is a mathematics vector calculus. So a little bit of mathematical equations, matrix notations, vectors. This was I was discussed these things in the first class. So you need to have some refresher over calculus, mathematics, matrix calculations. All those things is very much required for us. So this is where we need to have a little bit of vector calculus concepts. Okay. So please make a note of this. So we are expressing the Taylor's expansion in the form of a vector gradient and the Hessian matrix. Often a change in the function is desired when x star moves to a neighboring point x. Defining the change of delta f of x minus f x star, the above equation will become. So this is just rearranging the terms in a different way. Then a first order change in f of x at x star, denoted as delta f, is obtained by retaining only the first step in the above equation. So delta f is equal to gradient of transpose of a gradient vector f into dx, where delta x is a small change in x star. Note that the first order change in the function given above equation is simply a dot product of the vectors. Dot product of the vectors, gradient of f and delta of x. A first order change is an acceptable approximation for the change in the original function when x is near to x star. Please make a note of these things. Please make note down these equations. So it is very important now, because in the next slide I will have some simple problem to solve. Note down the terms properly, don't do mistakes here. Oh, next I will just take you for a simple problem. How to expand a function using a Taylor's expansion. Okay, so let us go to the problem statement now. Yeah, please unmute yourself, unmute everybody. I will take you to the problem because I want the solutions from your side. Please take a pen and a paper. Okay, so please note down this problem. Please note down this problem. Please note down this problem. Obtain a second order expansion for the function at f of x. Obtain a second order Taylor's expansion for the function at f of x is equal to 3x1 cube into x2. Function is f of x is equal to 3x1 cube into x2. At the point x star is equal to 1 comma 1. Hope everybody could able to get this problem statement. Mithun? Mithun, Sandesh, are you there?
Sir.
Yeah, please note down the statement.
Yes,
This is a problem for 8 marks. Okay. So everybody has to note it down and you have to get the solution for this problem now. Yeah. F of x is equal to 3 into x1 cube x2 at the point x star is equal to 1 comma 1. So the function is given. So when you look at this function, to obtain a second order Taylor's expansion for a function at f of x. So when you look at this function f of x, yeah. Who is this? Someone is asking the question. Yeah, who is this? Yes, sorry, I could not able to hear. Someone raise the hand. Do you have any doubt? Oh, now this is a second order Taylor's expansion function you're supposed to use. So because why second order here is, so when you look at the function here, f of x, which is a function of the two variables x1 and x2. Hence it is a second order Taylor's expansion for the function. Okay. So when you get a second order Taylor's expansion function, the gradient and the Hessian of the function f of x at that point x star 1 comma 1 can be determined using the equation. So here you have to determine the gradient vector and the Hessian matrix first. So because I will just go back to the equation here. So this is the equation for us. Okay, or you can use this equation also, gradient vector, anything you can use. Okay, so here what we want is, we want, if you look at here, so we want the functions which are in the form of a gradient vectors and also Hessian matrix. If you look at this equation, where is this? This equation, I'm sorry. This equation, if you look at here, okay, so here we are getting the Hessian matrix and the gradient vectors. Okay, so we had to make use of this equation and we had to get the solution for the problem. So now how do you do this? So gradient vector we have. So function is there. So partial differentiation of function with respect to x1, partial differentiation of function with respect to x2. So these two terms we have to get it. Okay. So what will be the equation you are going to get? And in that differential form, substitute x1 as 1 and x2 as 1, how we did in the previous class. Same thing, I want the gradient vector now first. So please tell me the gradient vector, what you will going to get it. Please solve it and get me the gradient vector. What should be the answer? I given the equation here. And here, partial differentiation of function with respect to x1 first. With respect to x1 and with respect to x2. And in that, you substitute x1 as 1 and x2 as 1 and get me the final equation. Anybody could able to get it?
9x1 square x2.
Substitute x1 as 1 and x2 as 1. Put it in the matrix notation. 9?
Yes, sir.
9 and
3.
Yeah, 9 and 3. Yeah. See, 9 and 3. So this is the expression what you will go into get it. So 9x1 square x2 and 3x1 cube. 3x1 cube. And when you substitute x1 and x2 as 1, 1, okay, then we can get the value of 9 comma 3. So this is how we will going to do the gradient vector. In the similar way, I want you to get the Hessian matrix. Hessian matrix. So please do that and get me the value of Hessian matrix. So Hessian matrix expression was like this. So last class we did this. Hessian matrix, this is the expression. Okay. So here we have only two variables. So therefore, first for these terms I want the matrix, Hessian matrix now. For that function, f of x is equal to 3x1 cube into x2. And put it in the matrix format and tell me the matrix element in that. Please do that fast. The Hessian matrix will be for you dou square f by dou x1 square. First term. Second term will be dou square f by dou x1 into dou x2. And the second row, dou a square f dou x2 into dou x1. And the fourth element is dou square f by dou x2 square. So this is the Hessian matrix for you. Only the first four terms because of the two variables here. So using that, I want you people to get me the Hessian matrix for this function. Hessian matrix for this function. Mithun, could you able to get it?
Sir, 18990.
Very good. Yes. Yes. So 18990. So this is the Hessian matrix for us. So look at here in the slide 18990, because this is basically Hessian matrix is a symmetric matrix. So this is the Hessian matrix. Okay. Now substituting these in the matrix form of a Taylor's expression using D is equal to X minus X star. Okay. We obtain the approximation for F dash X for F of X as. So this is what they have substituted now. So how we got this expression? So please, I will go back to the expression for the Taylor's expansion here. Yeah, this expression, please look at here. So f of x star, what you will going to get it? What you will going to get it when you differentiate, or if f of x star, in the sense you substitute x1 and x2 as 1 in the function 3x1 cube into x2. So when you substitute x1 as 1 and x2 as 1, f of x star will become 3 only, right? Are you able to get it?
Yes, sir.
So now I have substituted here first function. This is 3. This is f of x star. The f of x star, in the sense, in the f of x function, you substitute x1 as 3 and x2 as 3. x1 as 1, x2 as 1. I'm sorry, x1 as 1, x2 as 1. You will going to get 3. Okay. Next comes, so equation here, Taylor's expansion series. So where you are having here, yeah, plus I have got. So it is the transpose of the gradient vector. Transpose of the gradient vector. Gradient vector was 9, 3 for you. Transpose of that. So 9, 3 transpose, and D is, so we have x minus x1. So two variables are here. So x1 minus 1 and x2 minus 1. So that is also in the matrix format we have substituted here. So you can see this here. So 9, 3, it is the transpose of the gradient vector. Okay. So D term I substituted in the form of a matrix x1 minus 1. So that's what we are taking. D is equal to x minus x star. So here x star is 1. So x here is x1. So D I am substituting it as x1 minus 1 and x2 minus 1 in the matrix form. This is the second term in the notation. Plus half into. So I will go back to the again the matrix notation here. So here half into transpose of D, H into D plus R. So this is the one what we will going to do it here. So we are expressing everything in this form. So look at here, half into transpose of D. D is what? x1 minus 1 and x2 minus 1 transpose into H. H is the Hessian matrix 18990 into D. Into D is x1 minus 1 and x2 minus 1. Of course, you neglect the R. R term is not taken here, where f of x3 is 3 has been used. So 3 is substituting x1 as 1 and x2 as 1 in the function f of x is equal to 3x1 cube into x2. Simplifying the expression by expanding vector and matrix products, you obtain the Taylor expansion for f of x about the point 1, 1. So now you have to do the matrix operations. We had to do the matrix multiplication, okay, and we had to get the final equation. So this, it will take time for you people. So practice and get the value finally, because I don't want to wait for completion, because it takes some time. So finally, see, after completing expanding the vector and matrix products, so you have to do the matrix multiplication. So if you don't remember, please learn that matrix multiplication and complete this. Okay. So then after vector expansion and the matrix multiplication, so this is the expression, this is the equation what you are going to get it. This is the equation. F of f dash of x is equal to 9x1 square plus 9x1 into x2 minus 18x1 minus 6x2 plus 9. Please make a note of this equation. Please make a note of this equation. This is obtained as a result of the vector expansion and the matrix product. Okay, this expression is a second order approximation of the function f of x is equal to 3x1 cube into x2 about the point x star is equal to 1 comma 1. Please make a note of this equation. This is the final equation, very important for us. Okay, that is, in a small neighborhood of x star, the expression will give almost the same value as the original function f of x. To see how accurately f dash x approximates f of x, we evaluate these functions for a 30% change in the given point 1 comma 1, that is 1.3, 1.3. F of x will give the value of 8.2, f dash x will give 8.2, and f of x will give 8.56. Therefore, the approximate function underestimates the original function only by 4%. This is quite reasonable approximation for many practical applications, in the sense how accurately the f dash x approximates f of x. So for that we have done the trial here, that is 30% increase. So instead of 1 we have put 1.3. So what is the final solution we have got is f dash x we have got 8.2, where f of x will get 8.5. I'm just running out of my time, so I will meet tomorrow. We'll solve other one problem tomorrow also. Okay, if you have any clarification, you can do so, but we have to